Welcome back. Let us begin a new lesson entitled Structures. We will see this lesson along 5 different sections, introducing the definition of structures, how to use them, what is a dot operator. Then we will see the typedef keyword, the sizeof operator. We will see how to pass structures to functions. We will see what is the rules over structures inside structures or inside arrays or arrays inside structures, and we will end the chapter with pointers to structure. As usual, before we begin, you can always check the description box in order to access the playlist of this course, and you can jump from one title to the other quickly using the timeline also in the description box. So let us define structures. A structure is a composite data type or record declaration that defines a physically grouped list of variables under one name in a block of memory. So let us take an example. This is Dr. Seuss belongings. They are of different types. Let us state a fish, an umbrella, a coffee cup, a book. So they are not of the same type. We cannot put them inside an array, so we choose to put them in a structure type. So let's see more technically what is a structure type. A structure type is defined by the keyword struct. A structure declaration is a template that may be used to create structure variables, or we can say structure objects or structure instances. So we define first a template and then we can create variables of this template. This template is also called a type. Members are the internal variables that make up the structure. Also, they are called elements or fields. So here, for example, Dr. Seuss belongings members or fields or elements are the fish, the umbrella, the book, the coffee, etc. A structure provides convenient means of keeping related information together. So the members of a structure are logically related. They are not typed related, maybe, but they are logically related. This is the general form of structure declaration. You begin by writing the keyword struct, then you provide your structure type a name. And then you list between curly braces all the elements or all the members or all the fields. This is the same thing. Type name, and of course every declaration ends with a semicolon. And after you close the curly brace, if you have variables of this type, you can declare them at once, comma separated, and you don't forget to mention the semicolon because this is also a type declaration. Let's take an example and let's suppose we want to define a type to represent information about employee. We want to represent his name. It is an array of 30 characters, his salary, how much he is paid, and his phone number. So we have 3 fields. We declare struct employee, curly braces, semicolon, and inside the body of the structure we declare the 3 fields, name, salary, and phone, each of a different type. They may have same type, we may have a mixture here. Notice here the name, we declared it as an array of characters in order to hold space in order to receive the name later. Let us don't forget again the semicolon because this is very important. If we want to declare variables of this type, we can, for example, say we can declare the data type alone and then declare the variables of this type. For example, this is the data type employee, and later I want a variable e of this type. I have to write struct employee, which is the type, and e is the variable. You can declare the structure type and the variable at once, as we have seen in the previous slide. Here, for example, I am declaring 3 variables ABC of the type employee, along with defining and declaring the type employee itself. And you can declare the anonymous struct type plus the variable of this type. I omit here the employee name, so I only have 3 variables ABC of this type, and later I cannot create variables of this type. Let us see how structure is represented in the memory. So here E is a structure variable of type struct employee, and I'm interested in seeing how is the memory going to store E. E is a variable, so as usual it is a box in the memory. It is a continuous number of bytes in the memory. But here E contains other fields, so it is a big block in the memory relatively to the primitive types. So I will represent E as a block in the memory. Inside E, the fields of E. Suppose now I have the structure employee declared type and I want to create a variable and at the same time I want to initialize it. I have two ways. One way is standard and the other is not supported by all the compilers. So let us check the first C89 style initializer. You can provide the variable declaration followed by the equal sign and between curly braces the value of each field of this variable. And you can notice this is a similar syntax to array initialization, and here you provide if there is an array of character, as usual you can initialize it at once. They are comma separated. Another initializer is the designated initializer. You can use it when you don't want to initialize all the fields of this variable. For example, struct employee E equal, and you say the designation. I am initializing dot salary, which is equal to this much, dot name, which is equal to Alex, and notice they are not provided in the order. You can omit some, you can mix the order, but you must state the designator. So omitted elements in this case are initialized to their default values, but you have to remember that this is not supported by some compilers. Let us see what is the dot operator now. Suppose I have struct employee, which is our employee type, and I have a variable E of this type also declared. Suppose we have initialized this variable or we didn't initialize this variable. We want to access the members of the structure variable. To do so, we use the dot operator. How? For example, we can say e.phone, which is an unsigned long integer, and I can provide the value because, as usual, this is a variable. The phone is a variable, but it lives inside e. So in order to access it, I cannot write phone alone. I have to say the phone of who? The phone of e. So e.phone equals a certain value. Another example, if you want to print this phone, you can print f%lu and you provide e.phone and again not phone alone. You can, for example, read the name and store it inside the name field of e by using fgets as we have seen in the previous chapter. But this time you don't read in name because there is no name, there is a field name of a certain variable e. So again you provide this field's name, e.name. Also, because name is an array of characters, you can use it as an array of characters. You can loop and iterate over this field. You can change characters inside this field, etc., etc. You can use the string functions of the library on this field. So let us finish this section by doing some exercise. We have to write a C program in which we define a structure type for students containing a name, an ID, and grades for 6 courses, and then declare a structure variable of this type and initialize it, and then calculate and display the student's average. So this is an easy exercise that shows us how to use structures. So I go to my IDE and I create my structure type named student. Struct student. I have to store the name. So again, remember, it should not be char star, it should be star name of some size. And then the ID, I will choose to put it as an integer. And then we have 6 grades. It is logically to put them inside an array. I will not declare 6 fields named grade 1, grade 2, grade, etc. So the grades, let's suppose the grades are of type float. So float grades with s of size 6. And then they ask us to declare a structure variable of type student and initialize it. So I will declare a structure variable of type student, struct student. I will name my variable s, and initialize means directly after declaration I have to provide the 3 fields value. So I will provide the name and the ID, suppose 1, 2, 3, and the values for the grades. They are not inside another curly braces. They are given directly. So suppose he is very intelligent, so he takes 99.9 to finish this initialization. So this is the initialization, and later we are asked to calculate and displace the student's average. As usual, we can loop over this array for I equals 0, I less than 6, I plus plus. I want to summate inside a variable sum initialized to 0, and I will say here sum plus equal what? Sum plus equal the grades of I, but there is no grades of I, there is s dot grades of I. So sum plus equal s dot grades of I. After the for loop, I have to print the average, which is the sum over 6. So print average equal %f sum over 6. Let us compile and run our program, and we have the average executed. If I don't like the zeros after the comma, I can put, of course, 1.1 in order to take only one decimal. So this is average 88.7. Dr. Seuss is an intelligent student. We continue the lesson and reach section 2, which is typedef and sizeof, and let us begin by the typedef keyword. Typedef is not for structures only. Typedef is a keyword used in C language to assign alternative names to existing data types. It is not actually creating a new data type. It is assigning a new name to an existing type. The syntax is typedef, existing type, new name, semicolon. For example, typedef, unsigned long, ulong, semicolon. So ulong is a name now that can refer to unsigned long. You can define the field phone in our structure employee. Instead of using unsigned long, you say ulong phone. Both existing type and new name for this type can be used simultaneously. Another example, typedef unsigned int unit, because unit is more much expressive than unsigned int. A unit is of course a positive number. Typedef and structures. So typedef can be used to give a name to user-defined data types as well. For example, we can declare the structure type employee and give it directly another name emp. If I want to declare a variable e of this type employee, I can say struct employee e. I can also say now emp e. You can use the same type name to get rid of the keyword struct in the variable declaration. For example, if I use the same employee name here, it means instead of writing every time struct employee, I can now say only employee. Another way also, you can use it with anonymous type declaration. You can remove the name of the structure type from here and put it only in the typedef new name. So we can say typedef struct anonymous, and then we give it the name employee. And then I can declare employee E, of course. Beware, when the typedef keyword is present, you cannot declare structure variables at the same time of the structure declaration. So here, before the semicolon, the word employee does not mean this is a variable of this type. It means this is the name of this type. Let us talk now about the sizeof operator. Sizeof is a unary operator that generates the storage size of an expression or a data type measured in the number of char-sized units. It means if you ask size of char, it will return you 1. So its return type is size underscore t. Size underscore t is a typedef, but it is implementation dependent. But this is an unsigned integer. This is unary operator. It means it takes only one operand, and it can take either an expression or a data type cast. A data type cast is enclosed in parentheses. So let us run this demo. If we run this demo on my machine, I will get these answers. For the first two, those are variables and char types. So either you can put a variable name without parentheses, this is an expression, or you can put a typecast float between parentheses. So every two lines will give me, of course, the same thing. The size of a character is the same thing of the size of the variable of type character. So I have 114488. This is to show you how to use the operator sizeof. And finally, I saw what is the size of employee E. So I ask what is the size of the structure employee, or what is the size of a variable of the structure. This also will return the same answer, and it returned 48. So my floats are stored on 4 bytes or 4 character size. My unsigned long uses 8, and the employee structure itself uses 48. Notice here that if you run this demo on your machine, you may get other values. So attention, it is implementation dependent, and this is the reason why we use sizeof instead of using the sizes actually. We ask the machine what is your size for a certain type. Notice again that the 84 is greater than 42. So the size of a variable of type employee is not necessarily the sum of the sizes of its fields. It's for sure greater or equal to the sum of the sizes of its fields, and that's why also we have to use sizeof whenever we need to allocate a place in the memory to hold a variable of type employee. We will need this in the next. Allow me here to draw your attention to strcopy use, because I created an employee variable E and I wanted to fill the salary, the phone, so I filled them using the assignment operator. But however, for the field name, I cannot write e.name equal, and this will not work over strings. This will work only on the initialization. So I am obliged, in order to fill the name, to use the strcopy function of the string.h library. This is very important, and a lot of students make this mistake in the programs. Section 3, Passing Structures. Let us begin by passing structures through assignment before passing structures and function parameters. So let us consider this program in which we define a structure point with two fields of type integer x and y to make it simple, and then we are declaring two variables a and b of this type. We use the type def now. We are using the light syntax, and a is directly initialized with the fields x10 and y5. However, b is left uninitialized. We can later assign the value of A to B by writing B equal A, and this is the purpose of our slide now. So let us see. If I declare point A and B, I have in the memory my two structures A and B, with A initialized and B uninitialized. If I say B equal A, it means I copy the values from here and paste them here. There is no pointer here, there is a copy-paste operation. So B's fields will receive the same thing as A's fields. To make sure that B and A are independent in the memory, I will try to change the Y field of A and see whether it will reflect into P. So A dot Y plus equal 10, you can see that A dot Y is now 15 instead of 5. However, B dot Y is still 5. If you don't believe me, you can print both values and you will get 15, 5. Passing structure members. Now I want to pass the structure members and not the structure themselves to other function. Do you remember our function swap, which swap two given variables? I want to use it in order to swap two fields inside 2 points. I want to swap the a.x field with the b.y field. To do so, I of course have to pass the addresses of these fields. So let us see what happens in the memory. I have my variables a and b initialized to 1, 2, 3, 4, and I will now call swap, and as you know, the call must match the function definition, and this is exactly like an assignment. So we are assigning int star p1 to the address of a.x and not the address of a. Notice here, this is very important, the arrow that exits from p1 does not come to the address of the variable a, it points the beginning of the field x that is inside the variable a. So I pass the address of a.x and not the address of a. And the same thing here, int star p2 equals the address of b.y. And then the swaps work normally, as we all know. It receives the dereference of P1, and dereference of P1 will receive dereference of P2, which is 4, and dereference of P2 will receive 10. And then if we print the both variables, they are already swapped. So this is passing structure members. If you want to pass structures themselves, you have to recall also that the same rules apply. Recall that passing data from argument in the call to the parameter in the function behaves exactly like an assignment operation. Also, type of argument must match the type of the parameter to do the assignment operation. And here there is a particular thing you must take care of. To be visible from both caller and callee function, you must make global the declaration of the structure type. So here is an example. In this example, I have main that calls printSalaryRaise test, which calls printSalaryRaise. And here is the passing of the parameter of type employee between printSalaryRaise test and printSalaryRaise. I am declaring an employee and initializing it by giving a name, a salary, and a phone number. And then I am passing all the E to the printSalaryRaise. printSalaryRaise will also take a percent. It will apply the raise on the salary of E and then print the salary. I am printing also the salary from the caller and the callee to show you that the passing is like an assignment. So there is a copy of the employee inside each function. When you call printSalaryRaise, you are passing E. It is copied into the employee E declared inside printSalaryRaise with the same value, just like the assignment we saw 2 slides earlier. And then when you apply E.salary plus equal the raise, you are applying to the copied value that is inside the printSalaryRaise, and it is equal now to 102,000. However, the initial value inside printSalaryTest is still 100. Let's find the mistake in this program. I have my main in which I am declaring a variable named arg of type struct type 1. I am assigning its field A to 100. Let's see type 1, struct type 1. It has integer AB. It has character CH. So I'm giving A the value 100. It's fine. Then I am passing arg to the function f1, which receives a struct type 2 called param, and then it will print param.a. What is struct type 2? Struct type 2 is the same thing as struct type 1. It has the same fields in the same order, the same names, the same types. However, this is not the same type for the compiler. The compiler does not understand that they are the same. So here is the mistake. The type will mismatch, passing structure type 1 to parameter of incompatible type struct type 2. Let's begin the new section now, which is nested structures. Nested structures, let's begin with arrays of structures, and this is a most common usage. You can declare an array of structures by defining the structure type, and then you declare an array variable of that type. How? Let's take an example. In a company, there is more than one employee normally. So we can, for example, declare a 100 element array of structures of type employee. Let's define our type employee as usual, typedef struct employee with name, salary, and phone. And then inside main, for example, I can declare an array of 100 employee. So employee is the type, employee brackets 100, and the name of this array is employees with S. What is the shape of my employees array? I will skip for now that employee is a pointer to simplify the schema, and employee is an array of 100 elements, each of which is of type struct. So each element in the array 0, 1 until 99, each element can hold a structure of type employee. It has 3 fields: name, salary, phone. Name, salary, phone until 100. So for example, let's do something with this array. Suppose we filled this array with our employees, and we now want, for example, to print the list of the names of these employees along with their salaries. I iterate using, for example, a for loop with the index. I can also iterate using the pointer syntax, but let's begin iterating using the index. For I equals 0, I less 100, I++, print %s's salary, where %s is the element employee of I, dot the name, and print %f, where %f is the employee's salary. Nested structures. Members of structures themselves may be of simple type or of compound type. Compound type are one-dimensional arrays, multidimensional arrays, or even other data types. Let's take an example. Suppose we want to define the structure address that can hold the address of a certain person, which are the city and the zip code, for example. I can add this information to the employee structure. So I want, in addition to the name, the salary, and the phone, I want to know the address of my employee. So I can simply declare here a field of type address, address ADDR. And I can continue and declare E of type employee. How do I represent E? E will be represented as a compound type holding another compound type. Name, salary, and phone are fields. Name is compound. This is an array. Also, address is compound. This is another structure type holding two fields. So we are seeing nested structures, a structure inside another structure. Okay, now how do I access, for example, the zip code field that is inside the address field that is inside the variable e? e.addr.zipcode, and I can, for example, assign to it the value 3256. We reach the final section of this chapter entitled Pointers to Structure. C allows pointers to structures just as it allows pointers to any other type of variable. Example, I can have a pointer to my structure employee. I declare it employee star PE, knowing that employee is a typedef. There are two primary uses for such a syntax. First, to pass a structure to a function using call by reference. For example, if I want to change the original structure variable, we have to pass a pointer to this structure variable. And the other will lead you to many more interesting places when you can create linked lists and other dynamic data structures that rely on dynamic allocation, which exactly happen to be the subject of our next chapter. But before you go to those places, I want you to take with you a tool that I will introduce now. It is the arrow operator. So let us try to access the members through pointers. Consider here our program, and I want to convince you that you need an arrow operator. Consider an employee variable E and an employee pointer PE which points to E. And now you are asked to assign to the zip code the value 3256, not through E like we did two slides before, e.address.zipcode equals blah blah, but through PE. So you have PE that references the structure employee. You need to dereference PE inside to reach this address. In order to enter inside the structure, you need then the dot operator, so you can get inside this compound type to go to addr.addr, and then you need again to go inside addr, which is not a pointer here, so a dot will be just fine. So dereference PE, all in between parentheses, .addr zip code, you can enter here now, equals 3256. However, this is a complicated syntax, and it becomes more complicated when we add more pointers and more nested structures. Can you imagine yourself writing parentheses, dereference, parentheses, dereference, parentheses, dereference x, close parentheses, dot y, close parentheses, dot z, etc.? This is because to go from a pointer inside a structure, you need a parenthesis, a dereference, and then after that you need to close the parenthesis and to make the dot point. This, in purple, can be replaced by the arrow operator. Why do we need the parenthesis? If we don't do the parenthesis, the dot operator is stronger than the dereference, so it will think PE dot, and PE is not a structure variable, so there is no field inside PE. So we are obliged by the parenthesis. Let me show you an example for those curious students who will not be convinced that there are cases that we can write this syntax here. Consider this advanced example which introduced the next chapter, in which we have a variable px of base type x star, and that points to the variable ax, which happens to be of type x, of course, which has one field inside it named py, and this field has the address of ay variable, and ay variable has one field also called pz and happens to address the az variable. And the question here is that there is the value 3 inside the I field inside the az variable, but we want a complicated task. We want via px, so suppose we don't know the names of these variables, we know only the name of the variable px, so via px we need to change the value 3 into 4. So you have to dereference px and then dot py, then dereference the whole to follow the blue arrow now with the blue characters, then dereference the whole with the magenta characters to access I dot I and then equal 4. So this is very hard. This is so much complicated. So we refuse to do this, and instead we need to write the arrow syntax. We want to write px arrow py arrow pz arrow I without any parentheses, any dereferencing, any dot operator. Notice here, focus on this box, how it will change. We can write this syntax, and this is a much better syntax. Thank you. Thank you, the arrow operator, for existing. So we can go back and revisit our problem, initial problem, and the same thing, we can use the arrow in order to dereference PE and then get the address, PE arrow address. Address here is not a pointer, so dot zip code, we can change the zip code value. Again, we can use the pointer to the structures in order, for example, to make changes happen on the original variable E. Let's revisit the old example, but this time we will call it not print raise salary, but raise salary, because it will indeed raise the salary, because we will pass a pointer to the employee and not a copy of the employee. So here, void raise salary will take an employee star PE and it will apply the changes on the PE using the arrow syntax. So this time, if you print the salary from the test, you will notice that it has really changed. Recursive structures. What is the meaning of the following syntax? Struct rec int I semicolon, struct rec r semicolon. And then we finish by the semicolon for the structure declaration. It is impossible to allocate such a variable of this type. If you declare a variable of type struct rect, it is impossible to allocate this in the memory because you will never know how much you need memory because it is infinite loop. So without pointer, recursive structures are not allowed. What about with pointers? If we write struct rec int I, struct rec star r, is this allowed? Yes, of course this is allowed. And this is the subject of the linked lists, which will be explained in the next chapter. So before we finish this chapter and we start exercises and lab sessions, let us talk about typedef and pointers. Typedef can be used also to give an alias name to pointers. For example, if I write int star x comma y, we all know that this declaration declares x as of type int star, however y of type int. If you don't want to make such mistakes, you can use typedef in order to define a type int pointer to be int star. And from now on, if you write int pointer, for example, x comma y comma z, it means all x, y, and z are of type int star. This is a use. Another use is the following. You declare typedef struct t int a comma b, which are fields inside the struct t, and then you continue star u. What does this mean? This means U is the new name for struct T star. So U is the new name for the pointer of base type struct T. So this declares U as an alias name for struct T star. Remember this, you will be needing it in the data structure course next semester. We will finish by motivating you to solve the memory state of this exercise and to deduce what will be printed in the screen. Can you draw the memory state? I will leave you think about this exercise. So we saw together in this chapter structures the 5 sections, the definitions, use, and the dot operator, the typedef keyword, the sizeof operator, passing structures, including structure assignment, passing member of structures, and passing structure variables themselves. We saw nested structures, array inside structures, structures inside arrays, structures inside structures, and we finally saw pointers to structures, and more importantly, we introduced the arrow operator. We saw lots of things in this chapter, and this is a very important chapter that is needed to begin with the linked list chapter next time.